Why are the forces T1 and T2 equal in magnitude? This is a question many students find tricky to explain. Let us break it down with a simple example to make it clear. Let's turn our attention to the string. The string pulls object 1 to the left with a force T1, and by Newton's third law, object 1 pulls the string to the right with an equal force in the opposite direction. Similarly, the string pulls object 2 to the right with a force T2, and object 2 pulls the string back to the left with a force of equal magnitude. The key idea here is that since the string is a physical object, we can also apply Newton's second law to it. In vector form, we can write T1 plus T2 equals ma. Then, in terms of projections, we get T1 minus T2 equals ma, where m is the mass of the string. Solving for acceleration, a equals T1 minus T2 divided by m. If the string has no mass, then T1 and T2 must be equal. Why? Because if they weren't, the equation would imply that the massless string accelerates infinitely fast and shoots past both objects, which obviously doesn't happen. The answer is T1 equals T2 because the string is massless. This leads to an important general rule. For any massless object, the sum of all forces acting on it must equal 0. Otherwise, it would experience infinite acceleration. Of course, in the real physical world, the string has a small mass, so T1 must be slightly greater than T2. How much greater? By exactly ma. Just enough to give the string the same acceleration as the objects m1 and m2. The smaller the mass of the string, the closer the values of T1 and T2. In the theoretical case, as the string's mass approaches 0, T1 would equal T2,